Hello, and thank you for joining this virtual session, this virtual micro app session. My name is Ray Baker. I work for Analog Devices, and I'm an RF specialist in the Southeast United States. I'm going to talk today about RF bias, amplifier bias networks. It's a subject that I think doesn't get the attention that it deserves, and we'll go into a few examples to make my point about some things you should pay attention to when you're starting an amplifier design. So the thing I've noticed over many years of helping RF customers is that we usually get the hard part right. We actually get the bias networks correct, we get the matching, we do all of the hard RF stuff, and then we so often corrupt a good design, perfectly good design, with a couple of shortcuts that we take on the bias networks. These are some of the expressions that I often hear as we're troubleshooting a bias network. Oh, that's easy. I can just change this part. Ferrites, that's what you need to do. So, these are some of the things that you'll often hear. If you find yourself saying one of these expressions, you should probably stop and think again. Let's take a little more look, pay a little more attention to this part of the circuit. So here's our first example. This is an HMC499. It's a K-A-band amplifier, and the customer showed me the picture that you see there from their spectrum analyzer. Hey, why is my amplifier oscillating? That's an old joke, by the way. All my oscillators amplify and all my amplifiers oscillate. So what's going on here? What's causing this? And worse, the customer said, I was really careful. I copied the reference design, your guidelines, your layout, your location, the type of capacitors. I copied all of that perfectly from your data sheet. And when I looked at the customer's design and hardware, yes, they absolutely did. They did a perfect job following all of our recommendations. So what happened? What's going on here? What went wrong? So the answer to that means, or lies in things beyond what you see in this data sheet or in the circuit. Let's look at that. Let's look a little deeper in the design and see what we find. And when we look that next step, what we find, this is a hybrid. We're using dye. And behind the hybrid on the other side, there were ferrite beads, some additional capacitors, things that you would say, hey, that's pretty good RF design practice. Normal kinds of things that you would customarily do. The problem is, if you look at the values of the ferrite bead they chose, at lowish frequencies, VHF, HF, that ferrite bead has an equivalent inductance of about 3 microhenries. And when you make an equivalent circuit now of the bigger picture, we find that effectively what the customer has done is put a resonant tank network on both the input and the output of the network that happens to resonate at exactly the same frequency that we're seeing on the spectrum analyzer. So it's a pretty good hint that we found the source of the oscillation. And this is very typical. Amplifiers are often unhappy if you hang high Q circuits on the input or output. Different amplifiers have different sensitivities, but generally speaking, if you see an equivalent circuit that looks like this, you've probably designed an oscillator, not an amplifier. So the fix for this was actually really simple. All we did is we swapped out the ferrite bead on the input side on the gate supply. We swapped that for a 47 ohm resistor. It removed that resonant circuit that was sitting there on the input of the device, creating that low frequency instability. And the circuit is then stable, everything is beautiful. So we can get away with this in this design because this is a FET-based amplifier. So there's essentially no current through that gate resistor. So we can afford to put some resistance there without really changing the bias conditions or really the behavior of the circuit in any way. So this was a really nice fix, but a great example of something that you should be mindful of. Don't necessarily stop with the first 1 or 2 components in your bias network. Go ahead and look at all of the components between your active device and the power supplies. So before we get into the next couple examples, I want to point out something that we often forget. If we're doing CW waveforms in an amplifier, that's a pretty simple problem for the bias network to handle. It has constant voltage, constant currents. Nothing is changing. If you're doing any kind of modulated waveform, especially if it's got any kind of amplitude information on the waveform, or a multi-tone waveform where there's an envelope, then we're going to have essentially the power in the amplifiers that the amplifier is delivering is going to vary. It's going to vary with time. As the amplitude, as the envelope varies with time, so must the DC power that's going into the amplifier. It needs DC power to make RF. If the RF goes up and down, the DC power, the power that we're providing the circuit, also needs to rise and fall, go up and down, and it needs to be able to follow that envelope. It needs to provide power when the amplifier needs it, and the amplifier is trying to make RF. So it's an obvious point, but it's something that I've seen folks forget many, many times. So with that in mind, let's look at our second example. This is a 30 to 500 megahertz tactical radio. The customer designed the circuit. They did CW testing on the bench. Everything looked perfect. The efficiency, the gain, it was stable. Everything about this amplifier is great. Then later at integration, they put real waveforms into it, and they happened to pick an AM waveform. So the envelope is going up and down. And it's a fairly wideband AM waveform. It was a 1 or 2 megahertz kind of information on that envelope, which means that we need to pass that 1 megahertz envelope through the bias network. That's a challenge when your minimum frequency is 30 megahertz and you're trying to pass 1 or 2 megahertz through LRF, that main bias inductor that we see in the drain circuit there. That's a problem. Those are not very widely separated frequencies. We want that inductor, that LRF, to be large because we're trying to isolate the drain from the power supply, and we're trying to do that at 30 megahertz. So LRF needs to be fairly large. The problem is that we're also trying to push a time-varying waveform, the envelope waveform, through LRF. So you've got this problem. It needs to be big, but it needs to be small at the same time. And the fact is, you just can't satisfy both of those conditions simultaneously. So what do? We need to throw a more complicated network at the problem. And if you look at this network that we've now put on the drain and you say, hey, that looks just like a low-pass filter, that's exactly correct. It is a low-pass filter. And we need to craft that low-pass filter much like we would craft any kind of arbitrary network. We want certain impedances at the nodes. We want certain roll-offs. We want it to have a high impedance looking into the network so that we have good RF isolation into the power supply. But we also want the impedance through the network to be low at our modulation frequencies. So by putting a multi-pole network here, adding some components, we can craft a network that meets those two requirements simultaneously. Just like a low-pass filter can pass certain frequencies and reject others, we're going to do the same thing with this bias network. We're going to pass DC and the envelope waveforms, but we're going to reject RF trying to go through this network. There's a couple of implementations of this classic circuit. The top circuit, we have Rs in parallel with the inductors. In the bottom circuit, we put Rs on the capacitors. It's very similar. Either circuit will accomplish. You'll see designers use both solutions, and be creative. You can mix and match this. But the general reality is just like in a filter, if you want a sharp transition between that rejection band and the pass band, you're going to need more sections. And the other thing that we realize is that we're stacking inductors here. Our LRF is going to be our smallest inductor. It's the one that's going to operate at the higher frequencies. Then as we move left to right towards the power supplies, those inductors will get progressively larger as we try to create some isolation, RF isolation between the input and the output there. So one of the challenges you find is that this network, if you actually sit down there and crank the equations for this network, you find out you end up with lots of poles and zeros very quickly, lots of resonant combinations. It looks easy, but it's not as easy as it sounds. So those resistors there are actually very, very important, and we need to design those. So here's a simple example taking that 30 to 512. The example 1 there is just L1. We're just using L1, a large capacitor. So this is the classic, very simple bias network solution. And you can see there we go. Essentially, it's just, J omega L. We're just simply seeing the impedance of that single inductor versus frequency. And of course, the problem we find is that if we make it small enough so that it's not resonant at 500 megahertz, then it's not big enough to provide any kind of isolation at 30 megahertz. So this is the classic problem. We want an inductor that's both big and, too big and too small. And we worry about any time an inductor impedance, especially an air-wound kind of inductor, if you see the J omega getting in that 500 ohms to 1,000 ohms range, you're probably above self-resonance. So we have to keep self-resonance of the bias components in mind all the time. So the next solution, example 2, and you can see that in the table, let's add a second inductor. Let's add a larger inductor there and see if we can get that impedance at low frequencies up a little bit higher. So we do that, and here we go. Now we have a problem. You see there's a very, very large resonance there in example 2. And it's going to cause a lot of problems. Our circuit is our amplifier is probably going to oscillate at that frequency. We put a very high Q network there, and it's not going to work, and the gain's not going to be flat, and the efficiency is going to change. All kinds of terrible things are going to happen there at about 50, 60 megahertz there because we've unintentionally created this resonance in the drain bias network. So what's the solution? Let's now add a resistor there. Let's put 56 ohms in parallel with L2, and something almost magical happens. We tame that resonance, and we're able to make a network now that has pretty reasonable impedance from very, very low frequencies to very, very high frequencies. It's well behaved. There's no resonances to speak of there, and this is likely to provide us a nice, stable network that has nice flat gain over frequency, good efficiency, and we can tailor this network to whatever envelopes and high pass, low pass kind of requirements that we might have to accommodate our modulation. So you can play with this in a circuit design tool. I usually find that you need to kind of play with the values to get the network the way you want. There are broadband inductors. Those should also be in your bag of tricks. Plain old wire wound inductors are great, but as I mentioned before, they tend to resonate when they're above about 500 ohms, J500. Conical inductors, we often see these in millimeter wave applications, things that are going up to tens of gigahertz. They tend to be large for low frequencies, but they should be in your bag of tricks. Tend to be lower current for the devices that are out there because they mostly serve these wideband mimic amplifiers. Ferrite inductors are what you reach for when you're trying to do big power at lower frequencies. You can get significant inductance, you can handle significant current, and these things are reasonably broadband with modest Qs, so they don't tend to resonate and cause problems. Here's the HMC8500. This is example 3. So we take the eval board out of the box. We test it at 2 gigahertz. It's perfect. It has good efficiency, good gain. Everything's great. we put a 100 megahertz bandwidth modulated signal into it, and we find that the EVM or the adjacent channel spurious is terrible. The reason for that is because we've got a 100 megahertz envelope that we're trying to push through basically a 1 microhenry inductor. It doesn't work. That envelope, the amplifier, I like to use the word, it needs to breathe. It needs to be able to reach into the power supply and say, I need a lot of power this nanosecond. And so that inductor, that L2, needs to be able to pass that envelope waveform to the amplifier so it can make the RF power. So what's the solution? We've kind of seen it. Let's take a look. Couple of ways you can do that. You can either lower the value of that inductor, or you could do this. You'll see this circuit very, very commonly used in wireless base stations, radar systems, and so forth. This tends to be a narrow band solution because we're pushing the bias through quarter wave stubs there. But you know, for 10, 20% kind of bandwidths, this is a perfectly wonderful scheme. And if you think about what's the video bandwidth, what's the envelope bandwidth that this circuit can accommodate, it can be very, very wide. We're really not counting on that LRF to provide the isolation. We get that through the quarter wave stub and the bypass capacitor. So LRF doesn't need to be a very large value. So this circuit can support very wide modulation bandwidths over modest RF bandwidths. The fourth example we're going to talk about, here's a L-band pulse radar. Again, same story. Customer says, hey, it works great, CW, but the rise time is terrible. Well, just like a modulated waveform that has an envelope needs to be able to breathe and needs to be able to pull current from the power supply when it's needed, the same is true of a pulse circuit. If the pulse has a very sharp rise time, that current needs to get through the drain bias network. It needs to get to the amplifier in order to make the RF power. So in this case, it was very simple. We simply lower the value of that LRF to something more reasonable. 30 nanohenries, it turns out, is a reasonable value. It gives you good RF isolation at L-band and yet allows a fast rise time on the output. If you think about this in terms of the classic LDIDT, we can actually plot that response, and this is what we should be able to see. The output should look pretty similar to this. This got us down into a couple 3 nanosecond rise time. The requirement was 5, so now we've got a circuit that actually does the job. So here's some things to think about as you begin your amplifier design. Don't stop with just the RF considerations. Look at your bias networks. Think about your waveform. Think about your rise times. Think about what that modulation bandwidth is. And make sure that you craft a bias network that can accommodate that. We have both RF requirements. We need to make sure that we're not presenting low frequency loads, that we're isolating the power supply at RF frequencies, but we also need to make sure that we're giving the amplifier energy, that we're allowing it to draw current out of the power supply in order to make that RF waveform. So again, these are some things to consider. It's not an exhaustive list, but if you work through these questions, you're probably going to be successful. I've tacked on a few references here. That first application note 1368 is a really good one. Ferrite beads are, I think, very misunderstood. They're wonderful devices, but they need to be used correctly and chosen correctly. There's a lot of different flavors and powders and muse and frequency behavior. So anyway, it's not a trivial thing to pick an appropriate ferrite bead or ferrite product in your bias network. The AN 2021 there, the next one, that's a brand new application note on our website, analog.com. It was written by one of our really fine application engineers. Some really good insights that are absolutely pertinent here to this discussion. So, and I encourage you to take a look at the other ones as well. I think you'll find them useful. And again, if you know, my take home here is pay attention to the bias networks. There's some subtle things, there's some subtle requirements there that we often forget about that extend beyond the RF realm. So Thank you very much for stopping and viewing the presentation, and I hope you find it useful. If you wish to contact me, you can reach me at ray.baker@analog.com. Thank you.